What if the next revolution in energy does not come from a bigger factory, a more powerful machine, or a breakthrough battery? What if it comes from a shape that scientists discovered almost 2 centuries ago, a shape that spent most of its existence as a forgotten curiosity until it suddenly became a threat to one of the most successful technologies on Earth? Because right now, hidden inside laboratories across America, a new kind of solar technology is challenging the assumption that the future of electricity will belong to the same material that has dominated for nearly 50 years. Silicon, the hero of this story, is not a company. It is not a factory. It is a crystal structure, perovskite. And the question surrounding it is simple. Can a material that was once considered useless become the technology that changes how the world captures energy? At first glance, the solar industry looks like a story of unstoppable progress. Look at a satellite image of Earth, and you can see the transformation: vast fields of blue panels stretching across deserts, rooftops covered with black glass, entire cities quietly harvesting sunlight. For decades, one material made that possible: silicon. But here is the first contradiction. The most important technology in modern solar energy is also approaching a limit. A silicon solar panel is an engineering masterpiece. It has survived decades of optimization. Scientists improved the surface. Engineers reduced wasted energy. Manufacturers created massive global supply chains. Yet every improvement became harder. The reason is not that engineers failed. The reason is physics. A silicon cell has a ceiling. It can only absorb certain parts of sunlight efficiently. The rest becomes heat. The sunlight arrives. The panel accepts some of it, and the rest disappears into the atmosphere. The lesson here is that the biggest challenge in energy is not always building something stronger. Sometimes it is escaping the limits of what already works, and silicon works. That is why replacing it is so difficult. The factories already exist. The supply chains already exist. The workers already know the process. From a distance, solar looks like a technology race. But the deeper you look, the more it becomes an industrial power struggle. Walk inside a traditional silicon factory, and the scale becomes obvious. The environment is controlled. The equipment is enormous. The process begins with raw material, but ends with something far more complicated: a perfectly structured crystal wafer. Silicon manufacturing is not simply making panels. It is maintaining a global machine that took decades and hundreds of billions of dollars to build. And that is where geopolitics enters the story. China did not dominate solar manufacturing because it discovered sunlight. It dominated because it mastered production. Factories became larger, costs became lower, supply chains became deeper. The world gained cheaper solar panels, but it also created dependence on one industrial ecosystem. The bigger picture is this: energy technology is never only about science. It is about who can manufacture the future. And then a strange possibility appeared. What if the next generation of solar did not require building the same industrial machine again? What if the future could be printed instead of forged? That is where perovskite changes the equation. Because perovskite is not just another material, it is a structure, a pattern, a way atoms organize themselves. Different chemical ingredients can create the same arrangement, meaning engineers are not trapped with one fixed recipe. They can adjust it, they can redesign it, they can tune it. The part most people miss is that this changes the entire philosophy of solar technology. Silicon is a finished tool. Perovskite is a platform. Imagine replacing a carved stone sculpture with a programmable printer. The difference is not just appearance. The difference is possibility. A perovskite layer can be extremely thin. A coating measured in nanometers can absorb sunlight that would require much thicker silicon. The material can potentially be printed onto flexible surfaces: windows, curved structures, vehicles, places where traditional solar panels were never practical. The image changes. Instead of seeing solar panels attached to buildings, imagine buildings becoming solar panels. A skyscraper no longer has only a roof producing energy. Every window becomes part of the power system. But here is the problem. A technology can be revolutionary in a laboratory and still fail in the real world. And perovskite had a serious weakness. It was fragile. Early versions degraded under moisture. Heat damaged performance. Sunlight itself created problems. The very energy source the material was designed to capture could slowly destroy it. Researchers had created a powerful solar technology that struggled to survive outdoors. It was a brilliant idea trapped inside a fragile material, a laboratory champion, a commercial failure for years. Perovskite existed in a frustrating cycle. Scientists announced breakthroughs. Industry waited. The technology seemed always close, but never ready. Then came the question that changed everything. What if perovskite did not need to defeat silicon? What if it could work with it? Everyone thought the battle was about replacing silicon, but the real battle was about combining strengths. The breakthrough was the tandem solar cell. Instead of forcing one material to capture all sunlight, engineers created a partnership. Perovskite captures the higher energy light. Silicon captures what passes through. 2 layers. One purpose. More electricity from the same sunlight. This changes everything because the future of solar may not be a war between old and new technology. It may be a merger. The image is no longer a factory replacing another factory. It is an existing solar panel receiving a new layer of capability. The old system becomes the foundation. The new system becomes the upgrade. Strategically, this matters because revolutions are easier when they do not require destroying everything that came before. A technology that works with existing infrastructure spreads faster than one that demands a complete reset. This is why perovskite has attracted attention from American research institutions, companies, and even defense planners. The battlefield is not only energy production, it is energy resilience. Look at a military base. The vulnerability is not always the generator. The vulnerability is dependence. A power source that is lighter, more efficient, and easier to deploy changes planning decisions. The military does not simply ask, how much power can we generate? It asks, how quickly can we adapt when the system around us is under pressure? That same logic applies to cities and industries. Energy security is becoming a strategic issue. A nation that controls advanced energy technology influences more than electricity prices. It influences manufacturing, transportation, national security, global competition. But another contradiction appears. A better solar cell does not automatically become a better industry. The technology must survive the hardest test of all. Time a panel on a rooftop does not live in a laboratory. It faces storms, temperature changes, dust, years of sunlight. The real battlefield is durability. And this reveals the invisible war behind every energy breakthrough. The material is only one part. The true competition is between invention and deployment, between a prototype and a product, between a scientific possibility and a trusted system, because investors do not finance promises. They finance reliability. Homeowners do not buy efficiency numbers. They buy confidence that their panels will still work decades later. The lesson here is that technology does not win because it is impressive. It wins because the world trusts it. That is why the next stage of the perovskite story is not happening only in laboratories. It is happening in factories and supply chains, in government contracts, in commercial installations. The question has changed. It is no longer, can perovskite work? The question is, can perovskite become an industry? And that question reaches far beyond solar, because every major technological shift follows the same pattern. A discovery appears. The old system resists. The breakthrough survives. Then the real battle begins. Scaling, manufacturing, adoption. The bigger picture is that energy competition is becoming a contest between systems. The nation that discovers a technology is not always the nation that benefits from it. The nation that builds the factories, controls the supply chains, and moves fastest may shape the future. This is why perovskite matters. It is not only about a more efficient solar panel, it represents a challenge to the assumption that the future must be built using the same methods as the past. A forgotten crystal structure could become a strategic tool. A scientific curiosity could become an industrial weapon. A thin layer of material could reshape the balance of global energy. But uncertainty remains. The question is no longer whether humans can capture more sunlight. The real question is whether the world can transform a scientific breakthrough into a reliable foundation for civilization. Will future energy systems be controlled by the nations that own today's factories, or by the nations that create tomorrow's technologies? And the bigger question, do you believe the next energy revolution will come from discovering new materials or from finding smarter ways to use the technologies we already have?